Okay, so here we're going to talk about a new gradient descent method called the conjugate gradient method. And that's going to force me to introduce something called conjugate directions, which are really special. This is actually a really nice, quite a beautiful mathematical method, I think, that uses some old school linear algebra. It's just really nice, and it turns out that it's really efficient too. So why should we talk about such a thing? Well, it's because the steepest descent method we've talked about before has got some issues. So it's a reliable method, and it's a really common starting method that people use in practice, so I don't want to be too harsh on it. But, you know, it's got a problem, which is that it can converge slowly. And the reason that it converges slowly sometimes is because it takes these steps down the cost function that are orthogonal. It always heads in the steepest direction down the surface, and so you always step at right angles. And that's not necessarily the most efficient thing to do, particularly when the surface is kind of steep, it's kind of elongated. So here, I take many more steps than I need to get close to the centre of this. So can we do better? Well, it turns out that we can. There's this thing called the conjugate gradient method, which actually, instead of taking a bunch of steps to get to the minimum of this cost function surface here, it actually can find the minimizer of an n-dimensional quadratic function, the quadratic's important, in no more than n steps. So, for a problem like this that's in 2D, it actually, will take a step somewhere and then head straight to the minimizer. So you find the minimizer exactly, and you find it in this case in just 2 steps rather than the 1, 2, 3, 4, 5, 6, 7, 8, whatever that's going to take to get close. So that's a huge cost saving. That's really, really nice. You also don't need to calculate the Hessian, which is good because that's a pain to calculate. You technically don't need to do any matrix storage or any matrix inversion. And it turns out that this method usually outperforms steepest descent. And actually, it's a more robust method than Newton's method. So it's got a lot going for it, and it's just mathematically really nice. So here's what it does in a 2D problem. So the green line here is showing you steepest descent. It's the same sort of picture as what I just showed before. So you take a step, you turn at right angles, you take another step, you turn at right angles, take another step, and you converge eventually towards the minimum, the minimizer of this cost function. Whereas the red curve here, the conjugate gradient method, the first step that it does is exactly the same as the steepest descent method. You take the steepest step down the hill and you end up in the same spot. But then what it does is it uses the actual geometry of this surface. So what I know about the geometry of my surface here, and it says, well, the best direction for me to head is going to be in this direction down the hill, right? And it actually heads to the minimizer of the function on exactly the next step. So this exactly converges after just 2 steps. In this case, it was a 3D function. This would converge after 3 steps, etc., etc., etc. So this is a really, really powerful method for these quadratic functions. So what's the problem that we're trying to solve? So it's all about quadratic functions, so it's limited to quadratics, which is, maybe sort of limiting, but you can approximate, as we've seen before, you can approximate functions by quadratics. So it's pretty, it's still pretty useful class of functions to look at. And the problem is to find the minimizer of the quadratic function. So the matrix A here, remember you can write a quadratic function in this form. The matrix A sort of describes the curvature of my surface. And then I've got this linear term, B transpose times T, B transpose times X, sorry, and then a scalar which doesn't really matter for the purposes of minimizing. So that's a problem that we're going to solve. And the algorithm, the conjugate gradient method that I'm going to develop over the next few videos, looks like this. So it looks scary at this point because it looks large, and I don't know what any of these terms mean. But it's actually pretty similar in structure to a general gradient descent algorithm or the steepest descent algorithm we've talked a lot about before. So the first thing to say is that just like steepest descent, where I have to calculate the gradient of my cost function, because I'm only looking at quadratics here, the derivative, the gradient of this quadratic function, well, that's just going to be differentiating the x transpose ax times a half. That's just going to give me ax, and differentiating the b transpose x just gives me b. So the gradient of this cost function is just ax plus b, which is really nice, simplifying things straight off the bat. And then what I do is I decide to take a step in the direction of steepest descent. So exactly the same as steepest descent. And so what I do then is I decide how far I'm going to step. So how far in this direction I should step, and then I take that step. Right, so that's that. That's exactly the same as steepest descent, or it's a general idea of a gradient descent. Then what do I need to do? Well, I need to find a new direction to step in, so I calculate my gradient again, and that's again exactly the same as steepest descent. But what I do that's a little bit different here is I calculate a different direction. So I don't just step in the direction of steepest descent. What I actually do is I calculate a new update to that direction of steepest descent, and then I head. I increment that, and then I head in this new direction u. That's not just negative of g. So the big question here is, how do I calculate these betas? Like, where does that come from? What's special about these directions? They're called conjugate directions. I'm going to talk later on about what's so special about them. But for the moment, just accept that this is a step in the algorithm. So, okay, and before we talk about the details, let's just summarise. The general structure of the algorithm there is similar to steepest descent. It's similar to a gradient descent algorithm, and it works well because these directions u are somehow special. These conjugate directions are special in a particular way that I'm going to talk about later. And the amazing thing about this is that on quadratic functions, it actually converges in no more than n steps. So the maximum amount of time that this algorithm is going to run for on a quadratic is n steps. That's going to take us some work to prove. We will prove it, but I have to firstly define what a conjugate direction is and tell you about these things. So we'll leave that for a later video. For the moment, let's just do an example to show that the algorithm actually works. So here's a particular quadratic function, which I can write in this nice linear algebra form, matrix form, where A is this matrix and B is this vector. And if this thing that I've asserted here, that the conjugate gradient is going to converge in at most n steps, then this should take no more than 3 steps, because there are 3 variables, x1, x2, x3. This should take no more than 3 steps in which to converge, no matter where I start. So let's start at 0, 0, 0, and then hopefully after 3 steps of calculating the algorithm, we'll end up exactly at the minimum. So we won't do hand calculation, we'll just use Matlab for this because we're a bit lazy. So here I've already typed in what the function is. So there's my matrix A, 3, 0, 1, 0, 4, 2, 1, 2, 3. There's my B, and here's my starting value, x. Now, before I do anything, let me actually just go back to the conjugate gradient method so you can look at it. The first thing to say is that the minimizer of this should occur when the gradient of q is equal to 0, right? So when, if I solve ax plus b equals 0, that should give me the stationary point, which should give me the minimum of this. So if I solve ax equals negative b, so a backslash b, right, if I solve that, that should give me the minimizer analytically of this cost function. And it does. So the solution that I'm looking for here is 1, 0, 0. Right? I should be able to converge to the minimum of this cost function at 1, 0, 0 in 3 steps. Okay, so then we'll just keep that in the back of our head, and then we'll see how we go. Okay, so let's just step through the algorithm. So the first step is to calculate this gradient g, which is a x naught plus b. Right, so that's the first step. I'm just calculating the gradient of the cost function as I've done before. So that's negative 3, 0, 1. Cool. And then I'm going to head in negative, in the opposite of that direction. So I'm going to head downhill rather than uphill. Okay. So heading into the algorithm here, I now need to calculate this lambda star. So that's g transpose times u divided by u transpose times A times u. I think I've typed that incorrectly, so if I calculate, except I have not put an equal sign, so that should actually give me the correct number there. So that's how far I need to step in this direction of steepest descent. And then what do is I calculate a new position x. So I take my x naught, 0, 0, 0, and I add lambda star L star times this direction of steepest descent u, and I get a new location, right? So that's where I am after one step. So it's the same step as steepest descent. Now I'm going to do something that's a little bit different. So now I'm going to calculate my gradient again. So at that new point, let's calculate the gradient, which looks like that. And now I'm not going to step in that because that would just be the steepest descent method. I'm going to calculate this new beta. So that's G transpose times A times U, times the previous U that I calculated, over U transpose times A times U. Calculate that beta, I get some number. Now I can update the actual direction that I'm going to step in is going to be negative G plus beta times U. Let's calculate. So that's my previous direction U, so the new direction that I'm going to head in is going to be that. Okay, I can calculate lambda star. Again, I can decide how far I'm going to step in this direction, and x is just going to be, take that step in that direction, special direction U, that's of length lambda star. So now I've done 2 iterations of this algorithm. In theory, if I do one more step of this algorithm, I should be finished. So let's see what happens when I calculate the gradient of my cost function. I'll calculate this special value beta, which I haven't really talked about how to get this yet. Calculate my new direction U, decide how far to step in the direction of that direction, how far to step in that direction U, that's lambda star, and then take that step, and lo and behold, I end up at exactly 1, 0, 0. And I decided before that that was indeed, I could calculate by hand that that's the true minima of this. So I've done exactly 3 steps of this algorithm, and I have converged exactly to the minimum of this, to the exact minimum of this cost function. That's the amazing thing about this. So it minimises exactly, not just approximately, but exactly in 3 steps, whereas steepest descent would have taken many steps and it wouldn't have even exactly converged to the solution here. So it's a cool method, and the next thing we have to do is some work. So that's the algorithm. Again, it is similar in form to a general gradient descent method, but the big thing about it that we're going to prove is this. So this algorithm terminates in at most n steps. So if I have an n-dimensional quadratic function, it will only take n steps, and then it will stop because it will have found the minimum and I'll be done. That's an incredibly powerful thing to be able to prove. We have to do a little bit of work to get there. In particular, I haven't told you what a conjugate direction is yet, so we need to define that first, and then we'll talk about how to construct conjugate directions, and then we'll eventually be able to prove this theorem. So that's where we're going, and we'll talk more about this in the next video.